Hey guys, Mr. Klein here with our second of three lessons in our chapter on Newton's laws of motion. If it's the second lesson, you can kind of guess what it's going to be about, Newton's second law of motion. So let's go ahead and let's get into it. Now, whenever we talk about Newton's second law of motion, we generally talk about force. And when it comes to, whoa, hey, that's a pretty big collision going on there. Usually we think of force, okay? Sometimes forces aren't exactly what we appear. You know, as you can see, you can have collisions involving a small amount of force. Whereas on the other hand, you have collisions with a whole lot of force. And what we're going to look at in this lesson is how Newton's second law tells us how much force an object has, how fast they're going, how much mass, how much the acceleration, and any of that stuff. And, you know, as you can see right here, Jadeveon Clowney has plenty of force as he hits that poor guy from Michigan. Okay, so let's go ahead and let's get into this. What is Newton's second law of motion? The thing is with Newton's second law, it's one of Newton's three laws that no one ever remembers, because the first one is, well, it's the law of inertia, and the third one, which we'll talk about in our next lesson, is, well, for every action there's an equal but opposite reaction. If you ask someone to talk about Newton's second law and give it in a nice succinct sentence, they'll be like, there's like a formula, but I can't explain it to you without going on a lot. So what I have right here is about the simplest thing I can put it. It's not a statement per se, but rather a relationship between force, mass, and acceleration. And it's best represented through a mathematical equation. Newton's second law is listed here. The force an object moves with is directly related to the mass of the object and by how much that object is accelerating. Okay? So let's go ahead and let's start a graphic organizer. It'll fill up your area for your organizer. And right here, Newton's second law of motion. The force of an object is directly related to its mass and its acceleration. So go ahead, in your purple box that you're going to color, go ahead and write down this definition. This is a definition of Newton's second law, and this is what we're going to work with. Okay, so a real quick review. Since we're talking about Newton's second law, and we're talking about force, we need to actually remember what force was. If you remember from our last chapter, we were talking about work, okay? And work has to do with force and has to do with energy and all that. Force is simply a use of energy to push or pull an object. Any push or pull is a force. Okay? Forces come in all shapes and sizes, but for Newton's laws, we'll discuss forces as this general concept. And remember, the metric unit of force is the Newton. It's named after Isaac Newton. Seems simple enough to me. So, as we're going into this, when we're talking about forces, we're talking about pushes and pulls of an object. It's what makes objects move. So let's go ahead and let's add this to our graphic organizer. I want you to put this red diamond right here, and I want you to leave it blank. We're going to fill it in later with Newton's formula, but I want you to put it right in here and as we move forward. So let's go ahead and let's talk about forces as a more general concept. If we look back to the lesson on work, we remember that no work is done unless an object is moving. Remember the guy shoving at the door from the new girl as much as he could? He couldn't get in because you were supposed to pull it, and he was pushing on it, and nothing was happening. He wasn't no work was being done because he wasn't applying enough force. Okay, why is this? Well, this is because of the concept of this term. We call it the net force, or the sum of all forces acting on an object. The net force is like what you get when you put all the forces acting on an object together. Determining the net force of an object gets complicated because there's lots of different friction and thrust and all of these things. So determining the exact force of an object can be difficult, but what we're going to do for this lesson is we're going to really simplify it down. Okay? It's really just addition and subtraction, and we're only going to look at it through very narrow parameters, just so you understand what the concept of net force is. So what happens is you take all the forces together and you add them up. If you come up with a number that's a 0, well, there's no movement. Okay, so there's no force. However, if you come up with any other number that tells you that the force is in balance, okay, there's no balance in the force, okay? Anakin Skywalker isn't here to save us and bring the force back into balance. The force is unbalanced, and as a result, because there's an unbalanced force acting on an object from Newton's first law, we know it will be in motion, or if it's in motion, it'll change its motion somehow. So let's go ahead and let's look at some examples. This is what physicists use whenever we talk about net force. So we use arrows, we call them vectors. And remember, velocity is a vector quantity, so it's speed and direction. And so what we have right here is we have two forces acting on an object. Generally, the vector, the longer it is, that's the magnitude, the amount of force being applied. We have 5 newtons right here. So we have two 5 Newton forces acting on an object, and it's pushing them to the right on your screen. 5 plus 5 equals 10. So it's moving with 10 newtons of force total. Well, what happens if you have an object and you have 5 newtons to the right and then 5 newtons to the left? Now, if you remember a number line, anything to the left is a negative number. Anything to the left is 0. So 5 minus 5 is 0. Well, if you have a net force of 0, that means the forces are balanced, and as a result, there is no motion, so the object is at rest. So let's try this again. Well, if we have 5 newtons of force to the right and 10 newtons of force to the right, we get 15 newtons. So it starts speeding up with more energy being added to it. Okay, well, what about 5 newtons to the right and 10 to the left? Well, 5 minus 10 is negative 5. The forces are unbalanced, but rather what we say is that the object is moving with 5 newtons of force to the left, okay? Or to the west if we're using a compass coordinate or something like that. If we have 5 to the right, 15 to the left, well, 5 minus 15 is negative 10. Okay, and this also works whether we're going up or down on the vertical and the y-axis. Okay, we have 10 positive, 5 negative, 10 minus 5 is 5. Okay, so plus 5 newtons of force going up. What we'll also use, and by the way, these diagrams come from the physics classroom, which if you want a really good high school way of explaining physics, use the physics classroom. It's really great. What we have is we have these vector diagrams right here, these net force diagrams. So the boxes are object, okay? So we have tension. We're pulling it up on a pulley, if you will, with 1,200 newtons of force. Now, gravity is pulling down with 800 newtons. So what is the net force? Well, what we do is we add 1,200 and then we subtract 800. Okay, 1,200 minus 800 is 400 newtons. Which direction? Well, we're pulling it up. Okay. On the other hand, let's say we have an airplane, okay? It's flying through the air. It's giving a lift. The lifting body is giving 600 newtons of force of lifting. Okay, gravity is pulling down with 800 newtons of force. Well, 600 minus 800 is negative 200. And for our purposes, we know positive would be up, negative would be down. We would say that the net force acting on this object that we represent in the square is 200 newtons down. So it would be going downward. And what happens when we get in different directions? Well, this starts getting complicated, right? So we have the normal force, which, by the way, the normal force, just saying, is the kind of related, it's the force that pushes up on the ground with you, that keeps you standing up. So let's say the normal force is pushing up with 50 newtons, gravity is pulling down with 50 newtons, and the force of friction, so we're pushing, is 20 newtons of force. Well, what's the net force? Well, 50 up and 50 down cancel each other out, so it's 0, which leaves us with 20 newtons of force left. Now, when you have unbalanced forces up and down, that's when you start changing directions and stuff like that, and we're not going to get into that for our purposes. So in my classroom, we're not going to get into it. If you're not from my classroom and you're watching this, you might have that in your class, and that's not in the scope of this video, so you might have to look somewhere else for that. So let's go ahead and let's go to our graphic organizer. The force of an object is directly related to its mass and acceleration. We have our diamond, and we're talking about the force. We talk about the net force, and the net force is the total of all forces acting on an object, okay? Some cancel each other out. If they cancel each other out perfectly, the force is balanced, it's at rest. If it's not balanced, then it's unbalanced, and as a result, we have some motion. Now, like I said at the beginning of the video, you can calculate the force of an object, okay? It's a mathematical relationship. Newton's second law of motion can be summed up in a formula, which is right here. F equals ma, or F is for force. And two other concepts we've talked about this year, okay? In chemistry, we talked about mass, and just now we talked about acceleration, or any change in the velocity of an object, okay? So this representation right here allows us to determine any force of any object if we know its mass and its acceleration. To determine the force of an object while an object has while it's moving, all you have to do is multiply its mass times its acceleration, and bam, you get the answer. And the answer in kilograms per meters per second, that's what we call a Newton. Okay, and in my class, we'll do the math and we'll only involve kilograms and meters per second for velocity. For other classes, especially in high school physics, you'll have to convert them. So let's go with a mathematical example. What would be a math equation without an example? Joel throws a water balloon at Jenna. The water balloon has a mass of 0.2 kilograms. And when it hits Jenna, it's accelerating at 24 meters per second. Joel really chucked it at her. What is the force of the water balloon as it hits Jenna before it breaks? So what force is it hitting Jenna with? Well, what we do is we take our formula. Force equals mass times acceleration. The next step we do is we substitute. We find out the mass, 0.2 kilograms, multiply it by 24 meters per second squared. Okay, that's your acceleration. 0.2 times 24 gives an answer of 4.8 newtons of force. Okay, that's not a lot of force overall, but there you go. That's what your answer. So remember, force equals mass times acceleration. Now, see that red diamond you colored earlier? Go ahead right now, and I want you to put the formula for Newton's second law right there. F equals ma. F equals m times a. So let's talk about some examples of Newton's second law as we go forward. Okay, because Newton's second law is sometimes it's kind of difficult to understand. So with these examples, I'm going to give you a hope that you can understand them better. So here's some examples. For example, you try to move a heavy object. You push on it. Okay, the object will not move. You won't move a heavy object if the net force of the object is equal to 0. Of course, because the forces are balanced. The reason why is you aren't applying enough force to move it. Okay, like what we have in this example right here, okay, with the gears moving, but I want you to pay attention to the man, okay? It looks like he keeps on pushing, right? Okay, so he's pushing, but is the wall that he's pushing moving? No, because he isn't applying enough force to overcome the other forces that are holding the wall up. As a result, the net force is equal to 0, and there's no motion. So let's go ahead and let's add this to our graphic organizer. We're going to have force, mass, and acceleration. Okay, so when we talk about mass, the more mass an object has, the more force it needs to move. Okay, you need more force to make it unbalanced in order to move. So let's look at some examples with regards to acceleration. The faster an object is accelerating, the more force it will have if it collides with another object. Which explains why if you have a golf ball and you're kind of tossing it up in the air, it's not really hurting when it hits you because it's not really accelerating too much. However, you stand about 5-6 meters away from a golf ball after it gets hit by a golf club, by a driver, it's going to hurt a whole lot more because the golf ball is accelerating so much more. Now, I like hockey. And so let's look at some examples of hockey hits. You should have hit the guy in blue, Dustin Brown. That's kind of the point. Anyway, he hits the glass with not a lot of acceleration, okay? He was just kind of skating up, he was gliding in, whoop, misses him, and he hits the glass, okay? So he doesn't hit with a lot of force. However, in this collision right here, Milan Lucic throws himself and hits. As a result of the collision, the glass on the boards around the ice breaks. Why? Because Lukic was actually going with far more acceleration, okay? The masses were probably about the same between Dustin Brown and Milan Lukic, but Lukic was accelerating a whole lot more. As a result, there was more force, and as a result, the glass broke. So let's go ahead and let's add this to our graphic organizer. The greater the acceleration, the greater the force, okay? So in other words, if you have two objects, mass being the same, the one accelerating more has more force. Okay, which leads to this point. Like I said, if they're moving at the same acceleration, the one with the mass will have greater mass, will have more force. If you think about it this way, okay, this explains why if you're playing football with your younger brother, okay, and you catch the ball and your little 5-year-old brother comes up and hits you, and you're like, oh, let me fall over to make it look like he tackled me. That's one thing. You're not being hit with a lot of force. However, a professional football player hitting you is going to hit you with a lot more force. Oof, yeah, he's going to feel that in the morning because that football player has a whole lot more mass whenever he hits, okay? And also, the football player from the Cowboys is running up he's accelerating too. And so when we have this collision, we have these changes in force and stuff like that. And it goes with there. So let's go ahead and let's wrap up this graphic organizer. If acceleration is equal, the object with more mass has more force. So let's wrap up this lesson. Newton's second law of motion is not a statement so much as it's a relationship. It's a direct relationship between mass and acceleration. The amount of force an object has while it's moving is equivalent to its mass times acceleration. And the total amount of forces operating on an object is what we call the net force. Because it's a force, a push or a pull, we use the metric unit of force, which is the Newton. Okay? Like I said, that force is a relationship between mass and acceleration. The more mass an object has, the more force it's needed to move. The more acceleration is needed for it to get going. And in terms of acceleration, the greater the acceleration of an object, the greater the force it will have. And conversely, if you have two objects going at the same acceleration, the greater force it will have because it has whichever one has more mass. Now, if you heard me, I kept on talking about acceleration and not velocity, actually speed. We will talk about in our next lesson when we talk about momentum and Newton's third law. So there you go. That's the lesson on Newton's second law of motion. I hope you enjoyed it. And if, as always, you have any questions, please let me know. And thanks for watching.